Hello again, this is Bruce Wallenberg with Lecture 7A. This particular lecture is broken into two parts, 7A and B, and this will be the first part. And this is called the Economic Dispatch of Thermal Units, Part 1. Now, this diagram is a very simplified diagram of simply showing three power plants, and here we have fuel coming in, we have a boiler B, we have a turbine T, and a generator, and we're putting out megawatts over here. So this is effectively power plant number 1, and the other two, of course, power plant 2 down to N. So we have N power plants, and they're all feeding into a common bus and into a common load. Now later on we're going to change that. We'll put transmission lines and so forth. But for now, we're considering that all the generation goes into one bus and directly into a load. We are ignoring any losses in the electrical part of the network, in the buses or anything. And obviously the sum of the outputs of the plant, these plants must equal to the load. And here's the problem that we've got, is that I've got the sum of the output. Now in this case, these F functions, this is cost. Okay, this is cost. And this is cost in dollars per megawatt hour. So it's really a cost rate. That's why that hour term is in there. A simple way to look at it is to say, well, if I run it for 1 hour, then it's the cost dollars per megawatt. And that's summed over all of the plants. So here it's written mathematically as a sum. So remember, this is a cost function. This is a cost function, and each plant, the power output is the determining factor in the cost. So more power, more cost. And last of all, we have this constraint, this equality constraint. And if you back to the chapter on constrained optimization, we labeled this equality constraint phi, and simply says that the total load minus the sum of all the power. Now here it's the power itself. The total megawatts subtracted from the load has got to be 0. So the load equals the sum of the power plants. And I've written it this way, you'll see very quickly, for a reason. I want this one on this side of that equation. So now we come back to our Lagrangian function, okay, that we talked about a few lectures back. The Lagrangian here is the FT, the sum, the total cost here, plus our Lagrange multiplier lambda times the equality constraint. And you remember that the two conditions of the Karush-Kuhn-Tucker conditions are: you take the derivative of the Lagrangian with respect to each piece of I, and that gives you a derivative here, df of pi dpi, or what we call the incremental cost, or more properly the marginal cost. Remember that you'll see the term incremental cost sometimes in books and publications on power systems. Technically, the economists that we work with say that that's a marginal cost. It's the derivative of the cost function at bus I, or at generator I. So it's dfi of pi with respect to pi. Now here we've got minus lambda. Remember, this phi had a sum, and I really do like to have this minus sign in here, because then the condition that 0 is equal to dfi dpi minus lambda means that the lambda is equal to the incremental cost. Okay, so that, and when I pull lambda on the other side, then the signs come out right. That's simply why I had that minus the sum here. The other condition of the Karush-Kuhn-Tucker is that the derivative of L with respect to lambda I'm back to my equality constraint. P load minus the sum of the PI equals 0. So this condition says that for ever many, if I have n derivatives, I have n equations here, and I have one more. So I'll have n plus 1 equations. And how many unknowns? I'll have n p sub i's and lambda. That's the n plus 1 variable that is unknown. So the mathematical statement of the optimum is that every generator is equal to lambda. We have not put constraints into our Lagrange function, but we do have to worry about the fact that the power output PI is between the minimum and maximum. And if you remember, we said that every power plant has a minimum that's not necessarily 0, and in fact it's usually not 0. It may be a number that's about 20% or 15% of the maximum. And so the PI has to remain within those two limits. Those are 2n inequality constraints. And then last of all, we have our inequality constraint. There's only one of those. Well, there's more to it than we've already gotten into. If the unit is not at either limit, so it's actually within, so now I don't have these equal signs in here. If it's literally between the limits, then the derivative will equal lambda. The derivative equals lambda. If the derivative is less than or equal to lambda, then we're at the max. So if the value for lambda that solves the problem turns out to be larger than the derivative of f sub I, p sub I at its max, then you know that generator is to be forced to stay at its max. Conversely or similarly, if the unit is at its min, then the derivative is greater than lambda. We can say that lambda is less than dfi dpi for that generator. Now what we're going to do now is show how we can use these rules to solve for the most economic. And what's the most economic? It's the minimum of the sum of the cost of all the generators. So what's the cheapest way to supply the load from that set of n generators? We'll start with a basic. This goes back to the lecture on the constrained optimization. So we're going to say, well, how do I set up economic dispatch as a simple constrained optimization? And remember, I had f of x1 and x2. Here's the cost functions. They're the generator megawatt output, and these are our f functions. Then we have a constraint here which says that the load minus x1 minus x2 equals 0. And then I have 4 more conditions that says x1 minus x1 max, that's the plus here, is less than or equal to 0. And x1 min is less than x1. That's the min so this is the max. This is the max condition up here. And this is the min. So that's the min condition. This is the max condition. Same thing here for the second, for x2. And so you end up with 4 more conditions, 2 for each variable, one constraint inequality for the max, 1 for the min. So these are inequality constraints, G1 and G2, and G3 and G4. They're all inequality constraints to get those generators between min or max, or either at the min or at the max. So now here is our Lagrangian. We've got the cost function, lambda times this omega. That's our equality constraint. So here it is written out. The cost function, lambda times the loading constraint, x1 and x2 minus, subtracted from the load is 0. And then we have the mu times the G1, G2, G3, and G4. So, and here they are down here. So I have 1, 2, 3, 4, 5 Lagrange multipliers and 2 independent variables. So there's 7 variables. Now condition 1 of the Kuhn-Tucker says that derivative of C1 with respect to x1, or C1 prime. Now look at, when you take the derivative with respect to x1, you get this, you get C1 derivative minus lambda, and then because you've got x1 in this constraint and this constraint, you end up with plus u1 minus mu2, plus mu1 minus mu2. Similarly for C2, or the x2 variable, it's the derivative minus lambda plus mu3 minus mu4. Okay, that's 2 equations. The derivatives with respect to x1 and x2. Here's my equality constraint when I take the derivative with respect to lambda. And then I get 4 more constraints. So I had, if we go back here, I have 1, 2, 3, and then I have 4, 5, 6. Okay, so I get 4, 5, 6. These are the derivatives with respect to mu, and you get these constraints like this. And so condition 4, remember we had to add this complementary slackness condition. This is condition 4. Says that mu1 times the respective function is equal to 0 and mu1 is greater than or equal to 0. Okay, so if this one is really greater than 0, then this part will equal 0. If this part is not 0, then mu is 0. And similarly for these other functions. So this is applying the theory we learned in the previous lecture on constrained optimization. Now, if all the mu values are 0, well then the derivative with respect to power plant 1 cost function, derivative with respect to x1, derivative of cost 2 with respect to x2 is equal to lambda, or these two are equal to each other. It says that if there's no generator at min or max, then they're all at the same lambda, the same marginal cost. However, if x1 is at its upper limit and x2 is not at any limit, well, that simply means that mu1 is greater than 0 and the mu2, 3, and 4 down here are 0. So then our equation says that derivative with respect to x1 of the first power plant's cost curve is equal to lambda minus mu1. And now this one is greater than 0. So that essentially says that the incremental cost at that point is less than or equal to lambda. And remember, we said that's at its upper limit. With respect to C2, the mu3 and mu4 are both 0, and so we're just at the value of lambda down here. If the opposite case, if with x1 at its lower limit, then x2 is greater than 0. And then the derivative function comes up and says derivative of C1 with respect to x1 is equal to lambda plus mu2. And then we say that this function up here is greater than lambda. The C1 is greater than lambda. So this is at its lower limit. So that in effect, lambda is less than this cost. If both variables are at their limits, the equality constraint is met, then the values of lambda and mu are indeterminate. If it turns out that we can balance the load and one unit is at its max, one unit is at its min, then you can't determine these values. That's a very kind of a strange point, but it can get to that point. But you can't. There's no such thing as lambda at that point, or mu. So in summary, then, minimize the sum of these cost functions, subject to the load minus all the generation equals 0, so the generation equals the load. And for every generator, it's got a max limitation, less than or equal to constraint, and a min. So these are inequalities for a maximum one and one for the minimum for every generator. And down here it says if x opt is less than its max and greater than the min, then its incremental cost is equal to lambda. If the x optimum is at the max, then the C prime is less than lambda. If the optimum is equal to the min, then the C prime is greater than lambda. In the textbook, the appendix also show how to convert inequality constraints to equality constraints by adding what are called slack variables. We saw this in solving for problems with linear programming. This was the way we did it. Well, you can do it here too. So instead of putting this less than or equal, let's make it an equality constraint. We'll just add an S right here, and we'll say S is always greater than or equal to 0. Well, a better way of doing that, okay, is to say I'm going to add S1 squared. Now, even if it were a negative number, it comes up to be positive because I've squared it. So S1 squared is this slack variable. And you notice that if x is less than x1, well then this part here is negative. This is a negative, and so then I add the plus slack in order to make it come out to 0. So I add this positive part out here, this s squared, and s1 squared, so that gets to be 0. So obviously if x1 is exactly equal to x1 max, well then the slack is 0. And you can use these directly in solving economic dispatch. Here's an example. Okay, I have two generators, three. So here's unit 1, 2, 3. This is coal-fired. These two are oil. 600 megawatts, 400 megawatts, and 200 megawatts. Here are the H functions, the BTU per hour. This is the heat rate function for these three generators. They're represented as quadratic functions. And we said that the load to be supplied is 850 megawatts, and here are the dollars per MBTU. The first one has got a 1.1, the other two are exactly $1 per MBTU. So here's my cost functions here. I've multiplied the first one by 1.1 and the other two are the same thing because the fuel cost is simply 1. So now I'm going to take the equations and I'm going to solve by taking the derivative with respect to P1, P2, and P3, and I'll say they're equal to lambda, and the sum must equal 850. Well, if I solve for lambda, note that what I have here, okay, if I take the whole works, I have 4 equations, right? 4 equations, 1, 2, 3, 4, and I have 4 unknowns that I'll just put unknown on Kn, okay? 4 unknowns, and the 4 unknowns are P1, P2, P3, and lambda. So I can solve them, and in this case they're linear equations. These are a nice set of linear equations. And if I solve them, there's the answer. Lambda equals 9.1, and then this is the solution for P1, 2, and 3. And it turns out that none of these are exactly at max or min. All of the constraints are met. Each unit's within its limits. That's the answer. There's the minimum cost. Now, suppose the price of coal now decreases to 0.9 instead of 1.1. Well, now I multiply the heat rate by 0.9 and I get this for the cost function. If I now go about the solution exactly as I've done before, I get this. I get a much lower lambda, and I get these three generations. The problem here is that P1, this one is greater than P1 max. That's the trouble here, and so let me just put greater than here. I'll put a greater than symbol. And P2 is below P2 min. So we've got a problem. This solution doesn't work, and we've got to start applying some other rules to get to the constrained solution. So let's set unit 1 at its maximum. So now I've fixed this. He's no longer a variable. I've got two variables, P2 and P3. Let's set P3. I'm sorry, back here. This should have been P3, and this should have been P3. I thought that was the case. There's a typo in the slide. This should have been this one is below its low limit. Now, so if I set this to its high limit and this to its low limit, well, then this unit has to be the remainder. So I got 650. Now this has got to be 200. Well, then I get a lambda like this, and if I calculate the incremental costs for units 1 and 3, this one is below lambda, and this one is also below lambda, and that means that the solution is no good. The incremental cost for unit 1 is less than lambda, so unit 1 should be at its max. However, the incremental cost for 3 should be greater if it's going to stay at its min. So unit 3 is not forced to its minimum. Now, the reason this looks like kind of contorted way to solve the problem, and the difficulty is Karush-Kuhn-Tucker does not tell you exactly how to go to the solution. You've got to get to a solution and test it, and then see if what prevails. Now, we could have put all those inequality constraints in there, and then we wouldn't have this problem. But let's keep going. So now let's set this one at its max and solve the two equations here. And we say that the remainder, the P2 and P3, have to give us 250 megawatts because I'm getting 600 out of P1. Now I get a lambda of 8.5, and I get these two values of P1 and P2, and we note that the dispatch meets the condition for P1. Its incremental cost at the max is 8016. Well, this lambda down here is 8567, and now this one here, which is less than, while F2 and F3 are both equal to lambda. Okay, so they're both equal to lambda. So the solution was that P1 was at its max, and P2 and P3 were not at limit at all. That becomes much less usable when there are many generators, many generators. And you might think, well, just put in all of those inequality constraints, though then you get a problem with many more variables and equations than perhaps when you've got hundreds of them. Not that that's an impossible way to solve, but I'm going to show you a much easier way of doing this. You do it as follows. You take and you draw. Here's the incremental cost, okay? And this should be dollars here. Dollars per megawatt hour. And that's the incremental cost, and this is P. And you got to make sure that these are all drawn on the same scale. And this is the value of lambda. And what we'll say is, I'm going to move this up and down. So I'm going to move this line up or down, depending. And here's wherever it intersects the cost, then I come down and I read the P. and I come down where it intersects and read the value of P down. Well, here it's below the low limit, so it stays at its low limit. This is its low limit, and it comes down, and I sum these up. Here's the sum, and that gives me the PR, or the required power. Well, if this is too low, if this is a small number, then I know that I have to move lambda up. I have to go up, and you notice that if I go up to a higher value here of lambda, now I will get a larger amount of power out of unit 1, a larger amount of power out of unit 2, and a larger amount of power out of unit 3. And you could just picture this as if you had these three graphs on pieces of graph paper, where again this axis has to be the same scale as the other two, and you could just take a straight edge, and as long as it's perpendicular to each one, or if you had them glued down to a drawing board and you had a t-square, you move the t-square up and down until the sum, and we take this new sum here, and we're going to look at the new value, and we're going to sum that up, and we're going to say, this one maybe is too high. Maybe I moved it up. Now I got to come down to this point. So we just go up and down like that. Well, now it turns out that isn't there a reasonable way to set up that search? And there's something that I have used for many years. In fact, if you look in some of the software that's on the website that supports our textbook, I call it a binary search. I automatically always build any economic dispatch using this binary search. And in the book we put a little footnote. This I learned from a colleague of mine when I was working at a company named Leeds and Northrop. The colleague is Walter Stadlin, who was a genius at solving many problems like this. And what he said was, okay, I start with a value of lambda. Well, if I know the maximum lambda that I can reach and the minimum lambda I can reach, well, the maximum lambda, okay, is the highest incremental cost of any generator at its max. When all the generators are at their max, look for the largest incremental cost. That's the largest lambda would ever have to be. Then I go to every generator at its min, and I say, well, what's the lowest value of lambda? Then no value of lambda. So I never have to worry about values of lambda above there or below here. And all I'm going to do is I'm going to start halfway between. So halfway from here to here, I'm sorry, from there to there. The halfway point is right here, and I'll test it. And when I test it, I'll say if the PI comes out some, remember wherever that value of lambda is, then I extend it across all the incremental cost functions, and I get a p-value. Well, if they're quadratic, that's a very easy solution because the incremental cost is linear. This is a very easy thing to come out with p sub I. And if the sum of all the p sub I, remember I dropped the p sub I and then summed them up, if that comes out greater than the load, we must reduce lambda. If it comes out less than the load, we must increase lambda. Well, at the very beginning, very beginning, I'm going to calculate something called delta lambda, and that's this spread. That's the min minus max over 2. So that's this. Delta lambda is this distance from here to here. So, and this is the same down here. Delta lambda, that's this, coming down to here. Okay, so I have two delta lambdas, and all I do now is I say the initial lambda was the min plus delta. Well, that's this halfway point up here. Lambda I, this is the start. Right? This is the start. Okay, that's the start. Lambda I is the min plus delta. Well, if delta is halfway up, then when you go add it to the min, you come up to this halfway point here. Now, if the load if the sum of the generation is greater than the load, you take the delta value and divide it by 2 and subtract it. If it's less than the load, you divide it by 2 again and you add it. And so either I'm going to go from lambda I, I'm either going to go up to this point where this distance again was delta lambda, the original value divided by 2, or I'm going to come down to a value down here, which is again delta lambda divided by 2. And then you test again. If you got up to this point here, you test it again. So we're just going around this one. But you'll notice that if I keep dividing by 2, keep dividing the delta lambda by 2, then the distance I move is half the distance that I moved the last time. And this process will always converge. It will always converge. And you could say, well, if the word, the number of bits in the word and so forth, believe me, with a 32-bit word or a 64-bit word, it'll converge. It'll converge, and you can set up a tolerance. I mean, you don't need to converge these things greater than 1/10 of a megawatt or 100th of a megawatt is fine. You can go to 1,000th of a megawatt. It doesn't really mean that much anymore, because now the cost, you're just minimizing down in the very, very small ranges. So you're just looking to see if the sum of the PI minus the load is equaling the tolerance. Then the algorithm is done. So you test it. You just keep testing. So the whole point is you go up, you go start here, you go up, you come down, you go up, and you keep changing smaller and smaller and smaller. And the fact that we're using these rules to test greater than load or less than load, chop the lambda in half, greater than load or less than, and it just keeps going smaller and smaller and smaller, and it'll converge to the correct economic dispatch. It's a very, very simple algorithm to program, this binary search. Very simple algorithm. You're always moving half the distance. I've seen people try to do algorithms where they try to accelerate and use multiple points and fit a curve to it. I'm warning you, those can get messy and they can get difficult to use. But this is a very simple algorithm. Thank you very much, and we will continue this lecture on 7B.